Hello, my name is Robert Smith and I'm with New River Community College, and today we're trying to calculate the standard EMF of a cell. In this cell, we have a silver electrode and a gold electrode and solutions of silver and gold. So we're not really worried about our nitrates. We're only worried about the ions that are associated with the electrode. The nitrates are what are called spectator ions. And we have it at 1 molar, which is a standard state. So we're not. This is to make the problem as straightforward as possible. So we need to start off whenever we're trying to calculate the standard EMF of a cell. That is, what is the E cell? That's what we're trying to figure out. So the first thing you'll want to do is you'll want to write your two half reactions, and you'll want to do it in the reduction form. So it would be Au3 plus 3 electrons yields Au. We know this is Au3 because the nitrate ion is a -1, and there are 3 of them attached to that gold. So when the nitrate dissociates from the gold, you end up with gold 3+. Okay? And similarly, we have silver plus 1 electron yields silver. Again, there was only 1 nitrate here, so 1 nitrate having a -1 charge, the silver must have a +1 charge. And we know from our standard reduction potential table that this half reaction is 1.50 volts, and this half reaction is 0.80 volts. And so what we need to do is figure out which species is the oxidizing species and which is the reducing species. The oxidizing will be our anode, and our reducing will be our cathode in terms of electrodes. So the anode and cathode, we're just going to put A and C. So for our anode, we simply look at our standard reduction potential and recognizing that on the table, the lower reactions, the ones near the bottom, have the ability to reduce the ones above it. So in this case, silver is going to, if you have the ability to reduce something, you are going to be oxidizing. So the silver is going to have to be our anode. So it's going to be oxidizing. And that means that our gold will be our cathode. This is for a galvanic cell, which means that we're moving it in the direction that is associated with spontaneous reactions. If you, this whole process could be reversed if you are considering what's called an electrolytic cell. And under those conditions, you're applying a potential to the cell to make it go in the other direction. But for this class and this point, we're just going to consider spontaneous reactions, so galvanic cells only. So the overall reaction, we have to consider that we need to balance our charge. So we need to multiply our silver by 3 so that the 3 electrons will cancel on either side. The key here is that regardless of what the multiplier is on silver, the standard potential here will not change. So even though I'm multiplying silver by 3, our standard potential is still going to be 0.8 volts. Okay, so our overall reaction will be 3Ag plus Au3 plus gives us 3Ag plus Au. Okay. And so there's a couple of ways of looking at how to do our E cell. The way that is standard in chemistry is that the E cell is equal to the the standard of the cathode minus the standard of the electrode, of the anode rather. The other way to look at it is look at the way you set up your oxidation and reduction reactions. So under this, because we flipped our Ag, our silver, so that initially it's all written in terms of a reduction. But because our silver is our anode, we flipped the direction. So it went from Ag to Ag plus instead of Ag plus to Ag. So we could say, let's put this in brackets. We could say that by doing that, we do reverse the potential. So we make it negative 0.80 volts. So that is a possibility. So that's the other way of doing it. But ultimately, it ends up being the same thing. So when you do this, if we identify the cathode and anode, we now can say that the cathode is 1.50 volts minus the anode, which is 0.80 volts, which gives us 0.70 volts. That's our E cell. If we do it this alternate way, where we take our anode and we don't even worry about the fact that there's an anode and a cathode, we simply know that we need to flip the direction of the reaction in terms of the which one is the species that's going to be oxidizing versus reducing. And once we identified the one that we're actually flipping, you could just say that E cell is equal to the sum of the E's. So this would be the sum of those two, which under this condition, we're going to put a star next to that. This would be the alternate way of doing it. So just be 1.50 plus negative 0.80 volts, which again gets us 0.70 volts. So regardless of which way you do it, it's going to get you the same result. It's just whichever one you're more comfortable with. This one is the standard that'll be used in future chemistry textbooks if you're interested in continuing with chemistry. But if you find this one to be simpler, then you're welcome to use this one at this stage.